All right, I guess it's time for us to start. Welcome back. We do have homework due tomorrow, and I would be happy to chat with anybody about it, especially if you are still unclear about what exactly the assignment is or how to send it in. Please let me know, and I will try to clarify. Is there any book about, any update about the textbook? Has anyone been able to read it? Yeah?
Yes.
Okay, so it seems to be working.
Yeah.
If it's not working for you, please let me know, but I'm glad to hear that. I mean, if it's working for one of you, probably it's working for everybody. So, excellent. That's good to know. Your big bucks at work. Isn't it amazing that you can read a book that you paid for? All right. So the homework is due tomorrow night. I hope it looks okay so far to everybody. Let me know if you got questions. Let's continue talking about the volumes of a revolution. So we are talking about volumes so far using these sort of disks. You slice the shape up. These are specifically for shapes which are created by revolving something or other across the x-axis. Now we are going to talk today about sort of variations on this, but the basic setup is revolving a shape around the x-axis and then finding the volume of that. If that's f of x, and I want the volume, say, from some x value a up to the end of b, or this thing is sort of like in the middle of the rotated picture here. That volume, there's a formula that we talked about last time. Its volume is integral, well, pi, you can put the pi on the outside or on the inside, f of x squared dx. This formula is basically pi r squared, where r is f of x. That's the reason for that. I mean, I would suggest you just remember the formula, but in case you're wondering, the reason why the formula is true is because this volume is built out of individual, you imagine this sort of individual little disks in there, if you were to slice this volume up into tiny slices, individual little disks. And that disk is a circle with some very slight thickness. But anyway, the area of this circle is pi r squared, where r is given by the height of the function, which is f of x. That's why we have pi times f of x squared. So that's where this formula comes from. And of course, you integrate from a to b. All right, we did a simple example of this last time. I want to try some slightly more interesting ones, and then we'll maybe go on to another thing also if we got time. So last time we talked about the volume of a sort of a trumpet bugle kind of a shape. How about, I actually kind of enjoy I like that this works out. We can let's find the volume of a sphere of radius, how about of radius 2? All right, now, of course, everybody knows isn't there like a formula for that? Yes, there's a formula for that. I want to do this kind of like by hand, though, without using the memorized formula from high school. Anybody actually remember the formula? Just so we can check the answer.
4/3 pi r cubed.
Yeah, 4/3 pi r cubed. So the answer should be, the volume is 4/3 pi r cubed. But, I want to do this for real ourselves, but just so that we can be sure. The answer should be, r is 2, so that should be 8, right? So just putting this all together, 32/3 times pi, right? That should be the answer if we do everything correctly. But anyway, let's try and set this up. So the volume of a sphere. Now, the only thing we know how to do is the volume of one of these kinds of shapes, which you obtain by revolving something around the x-axis. So we have to think about, can you get a sphere by doing that kind of spinny thing? And if so, what should the function look like that you spin that makes a sphere? Any ideas?
X squared plus y squared equals 1. Because it's a circle.
Yeah, you want a circle, right? If you start with a circle and spin it around, it makes a sphere. So the basic idea here is I want to start with a circle. Now we want radius 2, so I'm going to start with a circle of radius 2. And really, if you think about it, Really you only need kind of the top half of a circle, which is lucky for us because that's a function, right? If you take the whole circle, it's not a function, and that's slightly weird. But for our purposes, it will be good enough to just take the top half of a circle of radius 2, of course, right? And this, because we're going to want to do the integral involving this, we should write down a formula for this. The full circle would be something like x squared plus y squared equals 2 squared. That's the formula for a circle of radius 2. But if I want just the top half as a function, that would involve solving this for y. Can anyone say what would you get as a function if you solve for y here? This involves like doing the square root and some other stuff, yeah?
4 minus, like the square root of 4 minus x squared.
Yeah, I like that. The square root of 4 minus x squared. So this, if you start with this and solve it for y, that involves, 2 squared is 4. You subtract x squared over to that side, and then you take the square root on both sides, and you get this, right? Ordinarily, when you take a square root on both sides, you should worry about plus or minuses, but in this case, it doesn't matter. All I care about is the top half anyway, so I'm just going to take the plus out of the plus or minus. We don't care about the minus part. All right, so this is our function right here. This is our f of x, right? We should be able to just write this out as the formula, right? Pi integral f of x squared dx. And what are the boundary values? The a and the b, that would be sort of from left to right. What's the range of x values? Yeah?
-2 to 2.
-2 to 2, he said. I agree. That's because this is a circle of radius 2, which means it's on the far side it starts at -2 and it goes all the way up to +2. Yeah, excellent. And of course f of x is that thing in the box. Now I was temporarily a little worried about doing an integral involving a square root, but actually by some kind of magic we have square root 4 minus x squared, that whole thing squared. And what happens with the square root and the squared? They kind of kill each other, right? You have the square root of something, but then you square it. That is equivalent to just forgetting about the square root and the square. So it's pi integral -2 to 2, 4 minus x squared dx. And this is a, easy integral, right? No funny business in there. You can just immediately find the integral. You do the antiderivative as we do. So I go pi, pi is at the beginning. And then the antiderivative. Somebody want to shout it out?
4x minus 1/3 x to the third.
Excellent. 4x minus 1/3 x cubed. Great. And then I need to evaluate at 2 and -2. So let's plug it in. I'm looking for 32/3 times pi. I'm feeling good about the over 3. I mean, I have a 1/3 here, and I have a pi here, so, It could happen, right? 4 times 2 minus 1/3 times 2 cubed minus pi. 4 times -2 minus 1/3 times -2 cubed. All right? So this is everything has a pi in it. That's 8 minus 8/3 minus pi. This is -8 minus 8/3. Is that minus? It's plus here. All right? And then if you were to actually add this all up, this minus here turns that into a plus and that into a minus. Everything sort of adds together. Would you believe me if I told you? You do indeed get pi times 32/3. That's if you actually add the fractions together. Make a common denominator over 3. Everything works out great. All right, I don't know about you. I take some amount of satisfaction in being able to do a problem like this without using the old formula for the volume of a sphere. I mean, I think it's kind of neat that you can sort of do it by hand in this way. All right, excellent. Would you believe me? I don't think we need to go through the whole thing, but actually, you can try this. Try this at home if you're into it. If we use r just like as a variable, as a constant, instead of 2 in that problem. So what I'm talking about is instead if we just do integral minus r to r of square root r squared minus x squared, the whole thing squared, dx. If you do that whole thing again, but don't actually plug in the number 2 for the radius, just leave the radius as a variable the whole time, all the way through the whole problem. Anyone want to guess what the answer will be? I mean, that r will stay as a constant the whole time, and r will appear in the answer. You can't really do this in your head, but you could work this out if you like. You won't get 8s here. You'll get something like, well, I don't really know what you'll get, but it's something involving r's. I guess r cubed, right? Isn't that where the 8 came from? It came from 2 cubed. Anyway, would you believe me if I told you that the answer you'll get is actually this? Like, that's where that formula comes from. You can actually work this out totally in total generality, right? Rather than plugging in the specific radius. Try it out if you like. If you like doing this stuff all night long. It's not, I mean, doing that is not really much harder than what I just did with the 2 in there. It's not really any different. All right. I thought along these lines it might be fun to do a similar thing. Let's try this for another common shape that everybody knows about, a cone. Let's try it for a cone. So I mean a cone, like a circular thing at the bottom, right? And then a triangular kind of thing going up the top. Everybody knows what a cone is, right? The important quantities involved in the cone would be the radius of the circle at the bottom, which of course I'll call r, and then the height of the cone, which I will call h. And there is a formula for the volume of such a thing. Anybody remember this formula? By the way, I don't expect you to have these formulas memorized, but every so often there's somebody who actually remembers these. This is not the kind of formula that I typically have memorized either. This is 1/3 pi r squared h. That's the formula, all right? Pi r squared is the area of the circle on the bottom. So what we have here, the volume of a cone, apparently is the area of the circle on the bottom times 1/3 times the height. Does that seem obvious to anybody? The answer is no. Actually, to me, there's no good reason why that ought to be the correct formula for this, but it just is. But I would like to try to actually work this out in complete generality. So can we actually derive this formula out of nowhere by doing this sort of revolution volume kind of a thing? So let's try to get this formula. Let's derive this formula. All right. The way to do this in terms of a volume of a revolved thing, you have to think about how can you get this cone by revolving something or other. You know, the sphere, in the way that we set this up, the sphere was obtained from a circle, really a half circle, and then you spin it around. How do you get a cone? By spinning something or other around. Yeah?
Use a straight line.
Yeah, how about a straight line? Now, the way that I drew the cone here is not very helpful, but if you think of a straight line like that, right? If I revolve this around the x-axis, it actually does make this kind of cone that we're talking about, right? And so we are going to start with, our f of x is a line. What are the boundary values for my integration? They are, from here to here, the a to the b. What's the a? That's 0 on the left side. You might as well put it at 0. And then what about the b?
6.
I heard someone say h. I like this answer. All right? This distance here, you got to ask yourself, what is that distance? It actually doesn't have a specific distance, but that is the height of the cone, which we are calling h. And so my integration boundaries will go from, I wrote a there. I meant to write a is 0, right? And the b is h. So when we eventually do the integral, it's the integral from 0 up to h, which is a little weird to have a variable inside of the boundaries, but no problem, all right? We should be more specific about the f of x. I said f of x is a line, but if you want to actually use the integral for this, we have to say very specifically what f of x is, like what is the line? Anybody have any ideas? Or a part of an idea? I don't think it's not easy to just immediately tell me what the equation of that line is, but that's what I'm looking for, the equation of the line. What's the equation of this line? I mean, in general, if you ask me the equation of a line, I'm going to try to do like the slope and the intercept form, I guess, which is actually fairly convenient for this one. Can anyone say that line, what's the y-intercept? It's 0, yeah. So if I do, you know, y equals mx plus b. Now I'm thinking specifically about the line up top, right? Let's not talk about the other one, because all I care about is the one on top. That b right there is going to be 0. All we need to know really is the slope then, right? The slope. Of course, this is the rise over the run. I think the run is already labeled on the picture. What's the run here? H. Yeah, that's the horizontal distance that this line is going across. So that's h. How about the rise? That would be this. So that horizontal distance down there is h. What about this distance, the amount that it goes up? That is r in my original cone, right? That's the radius of the circle which defines the cone. So there you go. That's the slope. All right. So that means our function is f of x equals, it's mx plus b, where m is that, r over h. So this is r over h times x plus b, but that's 0. So it's just that. This is the equation of that line. All right. This is a little confusing because I'm leaving r and h both as sort of unknown constants. So you imagine these as real numbers and you treat them like numbers, but I'm not going to write any specific values in there. All right, are we ready to actually, go through the integral? Let's try it. So the volume should be pi integral a to b f of x squared dx, right? Plug everything in. The pi is pi. A and b are the boundary values. They are 0 and h. And then I have f of x is r over h times x. That thing squared dx. And now it's just a matter of simplifying and doing the integral. And keeping your wits about you with the weird r's and h's inside there. Remember, inside this integral, x is the only true variable. R and h are just constants. All right? So the first thing I would do would be to square up this whole thing. Right? Everything in here is multiplied or divided, so just everything you see gets square on it. So it's r squared over h squared times x squared. So I got pi integral 0 to h r squared over h squared x squared dx. All right. Anybody want to suggest, can we simplify this at all before trying to do the antiderivative? Yeah?
Can you just bring r squared over h squared to the outside?
Yeah, right. R and h are constants. And so r squared over h squared, that's just a constant, being multiplied on the inside, so we can bring it to the outside. So this is pi, and then r squared over h squared, integral 0 to h, x squared dx. And now this is an easy integral, slightly weird because of the h up there, but doesn't really matter. So I do the integral. So pi h squared on the outside. I left out the squared there. Pi r squared over h squared. And then doing the antiderivative gives me 1/3 x cubed. And I'm going to evaluate at 0 and h. All right, plug in the h. I get pi r squared over h squared 1/3 h cubed. Subtract. Plug in 0. Actually, when I plug in 0, I'm going to get 0 for everything, but I'll write it out. Pi r squared over h squared times 1/3 times 0 cubed. So actually that whole second part of the evaluation is all 0. And the first part is the answer, which we can simplify very slightly. We have h squared in the denominator and then h cubed over here. They will cancel partially, leaving behind just h, 1h. So my final answer is pi times r squared times 1/3 h. And that really is the same as the formula that you learned, or maybe you didn't learn, I don't know. That's the old formula for the volume of a cone. All right, pretty cute, I would say, that you can actually create these formulas out of nowhere as integrals. All right. Great. I got 2 little variations on the general setup, and then I have some for you to try. So one variation is, these are kind of similar to the variations that we talked about last time for areas between curves. Sometimes, so variations, which can make things slightly harder, although it's the same basic idea. One thing is, what if you are revolving around the y-axis instead of revolving around the x-axis? Then you have to do things slightly differently. For example, how about the volume obtained by revolving this parabola, y equals x squared, around, sorry, that's hard to read, the y-axis from, let's just say, y equals 0 to y equals 1. So the picture I'm talking about is the standard parabola. Sorry, I missed the origin. Check it out. Here's what you do when you miss the origin. Just do a little of that. Yeah. All right. And then revolved around the y-axis. So, and it says from y equals 0 to y equals 1. So that's playing the role sort of my A and the B. And then you take this portion of the thing and you spin it around that way. That's the volume that I'm talking about. This is a three-dimensional shape. It's kind of like a three-dimensional version of a parabola. Anybody heard that there's a name for this shape? This is, yeah?
Is this shell?
That's not what I was going for. It's kind of shell. I don't know. Like a three-dimensional version of a parabola is called a paraboloid. Tell your friends. That's called a paraboloid. This is like a little piece of a paraboloid. There's also something, I don't know if paraboloids really are very common in the real world. If you start with a hyperbola and rotate it around the y-axis, you get a hyperboloid, and that actually you see, like a hyperboloid is the shape of a nuclear power plant cooling tower, that kind of like hourglass sort of shape. That's a hyperbolic cooling tower. Anyway, I don't know if you care about that. Let's just try this. The whole deal is basically the same as usual, but you have to do everything kind of sideways. And just like we talked about a similar thing with the area between curves, you have to do it all as sort of x in terms of y. So your job in this case is to rewrite the function as something like f of y equals whatever, where you're using the variable, it's like x equals f of y. You're using y as the main variable instead of x. And then you do this volume is pi integral a to b of f of y squared dy, right? You do the same formula, but everything you're using y as the main variable instead of x. And the a and the b would represent y values, not x values. But that actually is appropriate for our setup here. Those two values represent y values rather than x values. All right, and in this particular example, it's not so hard. We were given the function, the original function here was y in terms of x, but we need to do it the other way around. So you need to solve this. So sort of like your first step should be to go far enough here. Solve that. It said y equals x squared. I want to transform this into x equals, what would it be here? The square root of y, yeah. If you want to solve that for x. And as usual, you should be worried about plus or minus or whatever, but in this case, it doesn't matter because I'm rotating this thing around anyway. If I only took the positive side of it, it would just be that half, but that's good enough for this problem anyway, so I don't have to worry so much about plus or minus. All right, so this is the function f of y, and then we more or less do all the same stuff. All right, so I think we can just plug in directly here. The volume is pi integral. What are the a and the b in this case?
0 and 1.
Yeah, 0 and 1. You just have to look at the original setup here. I straight up told you from y equals 0 to y equals 1. So the integration boundaries are 0 and 1, and then inside here goes root y. That's my function, but it has to be squared just because the formula for this volume thing is always pi times f of x squared, and then dy. All right. And this is an easy integral to work out. Again, conveniently, the square root will cancel with the squaring there, so this ends up just being y, dy, all right? And then we do the integral. Antiderivative of y is 1/2 y squared. So this pi times 1/2 y squared, evaluating at 0 and 1. Plug in the 1. I get pi times 1/2 times 1 squared, minus plug in the 0, pi times 1/2 times 0 squared. That's all 0, and this first one, 1 squared is 1, so my final answer is just pi over 2. I hope that's what you got. So this is a fairly, this was an easy one, but of doing it around the y-axis. It's really no different. You just have to translate your formula at the very beginning. Instead of y equals f of x, you write it as x equals f of y. All right, great. I got one more variation, which is actually, this variation is actually more interesting. And this, I heard some people talking about this. Another variation is what they call washers. And actually, if you look on our big list of topics, the checklist, this whole thing is called volumes by washers. We've kind of been doing the washers thing all along without me telling you, because all of the ones we've done so far have been sort of easy ones from this point of view. Here's an example of the washers thing. It's really not much more complicated than what we've been doing so far, but this is what you get if you rotate around the axis, but you start with the area between two curves. So here's an example. How about sort of a steep line and a not so steep line? This is y equals 2x. This is y equals x. And I want to take the area between those curves and rotate that area around the x-axis. You get sort of a, I don't know, like a cone-shaped hat or something. It's like this, and it has some, it's a round, you could wear this as a hat. It would look like a cone. But the inside of it is also a cone of sort of slightly smaller or something, all right? Find the volume of that thing. So this volume, we're going to do it in more or less the same way, but it's a little fancier because when you imagine slicing this shape up, as we always do, I imagine I'm cutting it into tiny little pieces this way. Each of those pieces doesn't look like a circle anymore. So this volume is made up of slices where each one is what does each slice look like? It looks like a washer. That's why they call this the washers. Each slice is a washer. I mean a washer like a thing that you put a screw through. No. Each slice looks like this, right? Each of these slices here, they look like one of these. So it's like a circle with a big hole in the center, all right? The fancy, these in calculus books, these are always called washers. More typical name for that shape in mathematics, this is like the mathematician's name for this shape. An annulus. Annulus is the name of that shape. I was teaching this class once. I asked, anybody heard like the mathematical name of this shape? And somebody said, isn't it that anal thing? Yeah, that's where the word comes from. This is, I would rather say an annulus. That's the name of this shape. All right, it's called an annulus. But anyway, it's in this context, this is always referred to as the washer method. So instead of the usual volume equals pi integral f of x squared dx, this whole idea comes from pi r squared, which is the area of a circle, right? to do this variation, we need to replace this. Instead of using pi r squared, we need to use the area of this annulus, right? Which is not the same as the circle because it has this big hole in the middle. How do you think about the area of this annulus? I'm going to think of it as a big circle on the outside, which has subtracted away a smaller circle on the inside. All right, so this annulus, it has, when you talk about the area of an annulus, it has sort of an outer radius and an inner radius, right? There's this outer radius and this inner radius. I'll just call this like outer and inner, right? And what's the area of the annulus itself? The annular is the adjective version of annulus, just like circular and circle. The annular area is pi times the outer radius squared minus the inner radius squared. All right? It's because I'm taking the full circle area, the outer circle, which would be using r squared, but then I subtract away the inner circle. So you subtract the square of the radius of the inner circle. All right? So that's the total annulus area. All right? And so where our volume formula for the washer thing, so this is the volume using washers. If you have sort of a function here and another function here, where this is I'll call this one f of x and this is g of x, and I'm talking about the area between these two things, and then you rotate this around, right? If you just think about which of these represents the outer radius and the inner, well, on this picture, the f of x is the outer because that's the higher up, and the g of x is inner. And so the volume using washers for this kind of picture would be integral, well, pi, integral a to b, and then it's f of x squared minus g of x squared. This is the outer radius squared minus the inner radius squared. Right? It's the outer squared minus the inner squared. This is how I usually think about this formula. All right, but otherwise it's more or less you sort of plug everything in and everything works out great. All right, that's the setup for the washers method. Now it'll be up to you on a test or something to decide which is appropriate. Like if given, depending on how I describe the shape, you have to figure out, should these be discs or should they be washers? And I think it's usually pretty easy to tell. Like this shape, you could tell it has to be washers because there's like this gap in the middle. But if it was totally solid in the middle, then you would just use the ordinary discs formula. All right. And if you like, you could also think in terms. I think somebody mentioned this last time. The ordinary discs formula is what you get for this if you just consider the inner radius to always be 0. Then this goes away, and you just get the old formula for the ordinary discs method. But anyway, let's try that specific example that I drew before. So let's do the volume. Sorry to scroll away from the formula. The volume of this shape. Now I'm going to do two straight lines here, the cone-shaped hat kind of thing. Let's do this, y equals 2x and y equals x. And let's go from the origin over to x equals 1 here. This area. And that area gets revolved around here. You get this cone-shaped hat, funnel-like thing. All right, let's find the volume of this thing. All right, this one is a fairly easy setup. You have to decide what's the outer function and what's the inner function in terms of the radius. But I think it's not too hard to see. The outer radius here will be the 2x one, and the inner radius will be the just y equals x. So my setup will be volume is pi integral. Now the x values, the boundaries for the x values will be 0 up to 1. So you can see that on the picture. And then I go the outer squared. So that's 2x squared minus the inner squared, which is just x, like so. All right. And that's really all there is to it as far as the setup. I mean, and then this ends up being an easy integral to do. So let's just work it down. Work it out. Work it down. Let's work it down. Right? Square out the squares, and now you can just like actually do the subtraction there. 4x squared minus x squared, that's 3x squared. Okay. Pi integral of 3x squared dx. And in fact, I can factor a 3 out of this integral. So 3 pi integral 0 to 1 x squared dx. And then do my antiderivative. X squared becomes 1/3 x cubed. So 3 pi times 1/3 x cubed. Plugging in 0 and 1. When I plug the 1 in, I get 3 pi times 1/3 times 1 cubed minus 3 pi times 1/3 times 0 cubed. That second part is all 0. The first part has a 1 cubed, which is just 1. 3 pi times 1/3, which is just pi. Straight up pi. All right? That's the volume of that cone-like thing. All right. I got one more variation before I give you all one to try. Any thoughts about this so far? I hope that this is seeming doable. We'll see in a few minutes, I guess, when I ask you to do one. One other way that washers will sometimes come up, and this can be a little complicated to think through. Let's try one in which I will say washers also come up if we rotate around a different axis. I mean, rather than the x-axis, I don't mean y instead of x. Can I say instead of axis? How about around a different line? Here's what I mean. Let's try revolve, use an example. Revolve y equals minus x squared between x equal 1 and x equals 2. Revolved around the line y equals 1. All right? So that's what I mean by rotate around a different line. That is not around the x-axis, but around this other line. So it would be helpful to draw a little picture for yourself, I think, just so you can make sense of what I'm talking about. So first of all, the function is negative x squared. That's an ordinary parabola, but going down. So from the origin, it goes down like so. And then I said between x equals 1 and x equals 2, so that's like here. This part of it, I'm talking about this area here. And revolved around the line y equals 1. This is the tricky part. Y equals 1 is up here, all right? And that's the axis around which I want you to rotate this thing. So what does it look like if you rotate this sort of vertically up here? It looks kind of like a, well, if I'm trying to think about what this looks like, first I would think about what's just like the straight up mirror image of that would be another shape like this, right? That's like its own mirror image across this line. And then what I get is a sort of circular rotated thing which looks like that. So it has sort of a big old shape like this. Does that make any kind of sense? If I draw any more, this will start to look like nothing. Anyone have a vision in your mind of what this shape looks like? Can you describe it? What is
Like the end of a trumpet, kind of.
the end of a trumpet? Yeah. Yeah, maybe. Yeah, I was gonna say it looks like a Christmas tree stand or something. Like it has a round hole in the middle, and then it has sort of tapered things on the outside, right? Yeah, it's kind of like a, I don't know what I was gonna say. It's a weird shape, but I hope everybody can see in your mind what this shape looks like. Although it's not entirely important that you can see what this shape looks like. What is important is that you can tell what is the outer function and the inner function. So first of all, I hope you agree, this, when you slice up this shape, the cross sections look like washers because you have this empty bit in the middle and then this sort of not empty bit outside. It looks like the washer's shape. You have to decide for yourself. So these are washers. We need formulas for the inner and the outer, the radii. We need formulas for the inner and outer radii. And this is a little tricky because, spoiler alert, neither of them is this, negative x squared, all right? They are, kind of similar to that, but that's actually not either of them. On the picture, the inner is this, and the outer is this, right? This is the inner, this is the outer. Or it might be more useful to draw it down here. That's the outer. That's the inner. All right, and you can think of it as either way. It doesn't matter. It's going to be, you might be worried about if it's negative or positive, but it's going to be squared anyway inside the formula, so it ends up not mattering. We need formulas for the inner and outer radii. Actually, one of those is easy in this particular example. Anybody have a feeling about it? Yeah?
Just one.
Yes. Which one?
Like the one below the.
Yeah.
line.
Are you talking about the inner or the outer?
The inner.
Yeah, the inner is 1 in this example. The part of this shape, which is like the hole in the middle, its radius is always 1 the whole time, right? As you go across here, this inner radius is always 1. So in this example, the inner equals 1. The outer, this has some kind of formula in it because the outer radius depends on how, it's like this height of this this part of the function, but as measured from here. Anybody got an idea? Yeah?
Do you plug your number, or you plug 2 into the equation?
You shouldn't. What I write here is going to be a function involving x's, so I'm not going to plug anything in because it of course this outer radius, like this one is the outer radius at the end, but I want a formula which gives me the outer radius at all times, at intermediate times. You got an idea?
Negative x squared plus 1.
He says negative x, I like this, negative x squared plus 1. Why'd you put the plus 1?
He was gonna say -1, but.
Okay. Why do you need the extra 1 or anything? Yeah?
Isn't that like the whole, like the inner?
Yeah, so it's sort of this, the distance from this axis all the way down to the curve is what I'm trying to talk about. Now the distance of just the curve right here is this formula, negative x squared, but you got to add on 1 to account for this extra part of the distance here. So this represents the distance from the rotation axis all the way down to the curve, which consists of 1 and then also this little bit of the curve itself. Yeah.
What if you did the outer like the other way?
Measuring up to the top?
Yeah.
Yeah. Okay. Then that's a little harder because you might be tempted to say that would be like 1 here and then plus x squared here.
Okay.
But actually this height is not x squared. It's more like x squared plus 2 or something like that because like x squared is a parabola starting from here. This parabola starts over there.
Yeah.
So
These.
that's you could work it out in theory that way. It's harder though.
Okay.
Yeah. Anyway, can we work this out? And then I have one like this for you all to try. So this is the outer and the inner radii. So my volume shall be, it's pi as always, integral from something to something. What are the integration boundaries? This is the range of x values that I'm considering. 1 to 2, right. Integral from 1 to 2. And now I go the outer, that's minus x squared plus 1 squared, minus the inner squared, which is just 1. All right. And now we have to do our best to work all of this out. 1 squared is 1, of course, so that's not a problem. What should I do with that, that first part there? This part here? Yeah, we really need to kind of distribute. Now, she said distribute. I think really what you mean is like sort of do the FOIL here. You should not, certainly not, you would not say distribute, meaning you just square each of those two things, which is not right. When you have a binomial squared, you have to do the FOIL thing to expand it. Anyway, this is pi here, and then I go integral 1 to 2. I'm just simplifying here. Negative x squared, it's like this, right? Minus x squared plus 1 times minus x squared plus 1, and then you do the FOIL. So when you do the FOIL there, I believe you'll end up with x to the 4 minus 2x squared plus 1. That's the FOIL on that guy. And then additionally, we have minus 1. That came from this extra 1 over here. All right, and that's a dx. All right, work it out. We can simplify, the 1's cancel, but other than that, this is not going to get any simpler, but it's fine. I mean, it's just a polynomial in there, so no problem, right? The integral of x to the 4 is 1/5 x to the 5, and then I go minus 2/3 x cubed. Plugging in 1 and 2. And the rest is just plugging in. So I got pi times 1/5 times 2 to the 5th minus 2/3 times 2 to the 3rd minus, same business, 1/5 1 to the 5th minus 2/3 times 1 cubed. That's that. Any thoughts about that? I'm feeling.
You don't have to simplify that, right?
No, I would not simplify it. Yeah. I'm looking at my paper. I have
Wait,
What
something.
about the two, it was like x to the 4th minus 2x squared, but then it's, when you integrate it, it's still 2/3. Wouldn't you have to take the 2 out first? Like,
2 all the way out of the integral?
That, but how is it 2x squared and then it's still 2/3?
Yeah.
You
So
did-
I'm leaving this 2 as a coefficient. I think this is okay. I if you have a coefficient in front of like in a monomial, this coefficient will stay like it is, and then I increase the power and divide by the new power. That's all right. Yeah. I'm looking at. I have a different answer on my paper, but I feel like this is correct what I'm doing now. All right. Sometimes I mess it up on my paper. Great. I got one for you all to try. I'm still thinking about that paper. I think maybe I did this. I think I made a slight mistake here. I'm sorry to say it. I feel embarrassed. This, I think I did this wrong. This really needs to be positive x squared here, not negative x squared. I'm sorry. It's because I'm talking about this vertical distance here. Can I scribble on here? I'm talking about that vertical distance. All right. You should, in order to find this vertical distance, you need to take. I mean, if I was talking about, say, the distance, say from, I don't know, x to y, the answer is y minus x, right? You take the bigger minus the smaller. In this example, y, I mean this value up here is straight up equal to 1. This value down here is negative x squared. So this, I'm sorry to do this, but I would rather get it right than just leave you with something wrong. This should have been 1 minus negative x squared, like that. The upper sort of extreme of this distance is at y equals 1, and the value at the bottom is negative x squared. Maybe he was right to begin with. Something, I don't know. And so, I mean, of course, this minus and minus can sort of cancel together. What it amounts to is x squared plus 1, not negative x squared plus 1. I'm sorry about that, although I'm glad I noticed before too long. All right, so can we just fix everything? I mean, basically, a bunch of these minuses should have been pluses. So this minus here should have been a plus. When I do the FOIL, it's a plus each time here. Still a plus on the x to the 4th, the minus 2x squared should be a plus 2x squared. And then everywhere else, just these minuses are pluses instead. Sorry about that. This minus right here should still be minus because that's part of just evaluating the integral at the end. All right, these can be a little tricky, which is, I guess, is why I messed it up. All right, let's try another. I have one for you all to try. How about, this is another similar type of shape, but I want a, this is just the line y equals x. But I would like to consider the region between 1 and 2 and up here. So that triangle, this is y equals x, and this is 1 here, y equals 1. And then rotate this triangle around y equals negative 1. So revolve triangle around the line y equals minus 1. All right. And again, you get something vaguely like a Christmas tree holder or something. So like this triangle, when you straight up reflect it, is a triangle down here, and then it's kind of a round thing having that shape. It's like a cone if you drilled a big chunk out of the middle of it, and you only take sort of a ring around the outside, cone shaped. That's what I'm talking about. All right, so let's find this volume. It's a lot like the one we just did. You should start by thinking about what's the inner and the outer radii. All right, see what you think. I will give you a few minutes. I'll maybe walk around and I'll try and give you some hints if you're having a hard time just getting it started. Somewhere x is here, so that distance is x. You don't want to do plus 2. Anywhere? Would you say that in?
So would it be minus negative
Easier in this case. That's just this distance.
the total distance, like of this, if you just pure units.
For the inner radius in this one should be a specific number, because that's the radius, this distance here of this inside part is just a specific number. The outer one depends on x. Just
Yeah, I think why just look at
Is
this?
anywhere?
We should check those days.
So you should think about finding a point on top here. And then subtract it. So here looking at, say, this is the height, so say this top value, which is just x, minus this value. this.
But the inner is two.
Okay. Yeah, that's good. This would be the distance.
Actually,
You think about.
the one minus the one.
That's actually.
Going on BS.
I would
The inner is two.
what's the value?
The outer is not x minus two.
The value, like of this line segment, the top value is given by the function, so that's.
Yeah, x minus
minus
two.
plus six.
Where's the x?
Yeah.
I like that.
Yeah.
Yes. This.
It's not like it's going down.
Actually doesn't.
No, yeah. What do you think?
Inner radius is the distance.
Yeah.
It's fine, yeah, I would like that.
So if you think about the outer radius is the
Yes,
distance.
so those are two, right?
Oh, so then that'd be 3. Oh, wait, maybe the inner minus outer.
Well,
Yeah, I think so.
on the very end, it's, yeah, so you wanna think about somewhere in the middle.
What?
What do you get for inner?
Here, I got
2.
inner's 2 and then outer is x plus 1. Well, it's like
How do you get
x
the inner?
Would be X. Okay, gotcha.
This is your point, so it's just up 1 and 2.
Okay, you go from
You wanna put it here?
Yeah, you do 1 minus negative 2.
Okay.
Because we know that it's.
Yeah, that's right.
This is
You mean
like
1 minus
middle,
negative
so
1.
it's
I kinda learned it in high school, like
Okay,
3
here.
bar
Do the
4.
same thing.
So I did that.
That's what I learned.
You mean 1 minus negative?
Like it's right.
You said minus negative.
Yeah, so you think of like
Yeah.
the height of this segment
You
would be
did.
the top value minus the.
So it's not, you're going from like the bottom, like here, to the bottom, and then
It's like
maybe
you're
that makes sense, okay. I feel like we're overcomplicating. Is that what you got?
Yeah,
Okay.
I have it, but
So
it's
now
like
you
my
got
logic is
something
right.
to
Can you
Okay,
explain
yeah, so
why?
I would say, the outer radius here is the height of this segment.
Yes.
There, all the way up.
No, I got
And
that.
that would be the length of that segment. I don't think so.
Where'd you get the final answer?
I had the same.
Outer radius, if you rate this,
I was just looking at you running through it. I was kind of just going based off of, like, I was just looking off.
So the inner radius, because we're rotating around, is
Wait, just
it's supposed to be here.
Oh, yeah,
These lines are drawn in different places.
So
Right,
it's,
so the inner radius goes from here to here.
yeah. So it's,
It's just the one that's going in.
so that's just gonna be, it's just be 1 plus 1, so 2.
It's two. No, I wouldn't think it would be two. I'm
Well,
not sure.
I was just thinking like this one.
Okay, yeah, that's one and that's one, sure, yeah.
Is that the way you can remember it?
Yeah, another way to think of it is this segment, to find the length, you would take this value minus this value. This value is
That's
this
like,
value.
okay.
One minus.
And then as far as the outer,
Yeah, so think of this in the same way. It's this value minus this value. This value is given by the function, so it comes back
it's the x minus 1.
It's 7:30.
to x minus
Minus
negative.
Thank you. The chalkboard. Thanks.
How's it going? Good going?
Shit.
What'd you say?
It's 7:30.
So the outer radius, I would think of as, it's, like, the height
It
of the
is
segment.
seven.
You would take the y value here, which is given by the formula, so that's x, and then you subtract this value.
Actually, it might be further wide.
I don't know, but I need to, I got you, so it's minus
I didn't
one,
simplify
five,
it.
one.
Cause the first one would be 8/3 pi, and then it's minus
We're just gonna find that it's 8 8/3 plus
From
4.
here to here?
So that's 12/3
And
plus
that's
3 minus.
this value is 1, and this is -1, so it's 1 minus -1, which is 2. And that's what you said. All right, let's talk about these. I went around with varying degrees of, I saw varying degrees of success. It wasn't helped by me screwing up the first example we did. So I will, yeah, let's see. So the inner radius, that would be the distance from the rotation axis here up to there, right? That distance as you move across is always the same, and it is always 2 in this example. As I was walking around, I saw people figured that out eventually. One way, if you really want to kind of overcomplicate or think about this very specifically, the height of this segment here would be the y value at the top minus the y value at the bottom. That is 1 minus -1, which equals 2. So this one, the inner radius is 2. Now you probably didn't think it through in that amount of detail, but the same detail is how you figure out the outer radius. The outer radius should be the value on top here, which is given by the function, minus this y value. And so I think of this y value up top, which is x, minus this y value of the axis, which is -1. So this says x minus -1, x plus 1. Yes?
Why would it not be +2?
Because it's not. Why would it be +2?
I mean, I don't know. I'm just like, I don't know. I just factored into 1.
Yeah, like for example, if x was 2, then this whole distance here is 3, right? Because if x is 2, then this part of it is height 2. And then I would add an extra 1 here, which gives me 3.
Doesn't the inner plus the outer equal the whole thing, so it would be plus x?
The inner plus the outer equals the whole thing. I'm not sure what you mean by that. The inner plus the
Equals
outer.
the whole radius for the whole thing, say there wasn't.
I would say the whole radius for the whole thing is the outer, isn't it?
Yeah.
Is that what you mean by the whole?
Like, well, yeah, I mean, but the inner is 2, and then x is on top of it, so we don't have that.
Right, but I think this may be similar to something you asked before. Like x, you feel like this function here is x, but the origin is down here. Remember?
Yeah.
Yeah.
So like, if I'm talking about a value, say right here, x for this point is actually like 1.5, something like that, right?
Yeah.
And so to get the distance to this axis, you add 1. You don't add 2. If you were to add 2, that would be too much.
Okay.
Yeah.
Alright.
It's a little confusing.
If you're plugging in the boundary, which is the 1, so you're like y equals 1x, so yours is 1.
Alright, that makes sense.
Yeah, I mean, if you just think about what the value should be on either end, I think you should be able to convince yourself that it should not be x plus 2. That's too much. Yeah.
Okay.
You're trying to get the function, the line, to the axis of rotation, like the little dotted.
Yeah, it's the difference. It's the distance from the function value, which is x, all the way down to the rotation axis, which is at -1. Yeah. I mean, to me, the easiest way to think it through is the top. If you want the length of this outer segment, it's the value at the top minus the value at the bottom, which in this case, the value at the top is x. It's not x plus 1, it's x. And the value at the bottom is -1. These are a little confusing. Anyway, can I, let's just real quick actually carry through the integration. So once you have it set up in these kinds of problems, that's often the hard part. So it's pi. Integral here will go from 1 to 2. That's the range of x values. And then it is the outer function squared minus the inner function squared. The outer radius and the inner radius with a dx. So this is pi, integral from 1 to 2. Do the FOIL here, x squared plus 2x plus 1, and then I go -4. So this is pi integral 1 to 2 of x squared plus 2x minus 3 dx. and then we just do the integral. So it's 1/3 x cubed plus 2 over 2x squared minus 3x, plugging in 1 and 2. So it's pi 1/3 times 2 cubed plus 2 over 2 is 1. So that's 2 squared minus 3 times 2. Subtract pi 1/3 times 1 cubed plus 1 squared minus 3 times 1. And that's my final answer. All right, a little tricky to set these up. That's what it takes. Any thoughts about any of those? All right, this is all I want to say for now about washers and discs and such. You'll have some more practice on these on the homework for next week. In our remaining 10 minutes or so, I think we can talk, just get started on the next thing, which will be the last of these sort of volume techniques. This is called volumes by cylindrical shells. And this is yet another strategy for finding volumes of shapes like this time by cylindrical shells, all right? And this is usually like an alternative. So there are certain shapes, many shapes that you can do by washers, you can also do by this shells method, and the other way around. Many times you can use this shells method, but you could have also done it using the washers. So the idea behind this one is maybe the standard picture of one of these cylindrical shells type problems is if I have a function, let's say like this, y equals x squared. I always like y equals x squared as a standard example. And I revolve this around the y-axis, but I want this part of it. So the area under the curve here, area under y equals x squared, from, let's go x equals 0 to x equal 1, and then revolved around the y-axis. All right. So what you get is kind of a weird-looking sort of bowl type situation here. It's a round thing which has like a basin inside of it, which is parabola shaped. All right. It's it's if you started with a round thing and then you like hollowed out a parabola from the inside of it. It's a bowl kind of a thing. All right. Now this thing, you could, if you like, turn it sideways and do the washers method. So if I were to make slices this way in this thing, each slice would look like a washer with an outer radius and an inner radius. But so you could do it that same problem in that way, but I want to do it in this other way. This is called volumes by cylindrical shells. So this involves, again, slicing it up into little bitty shapes, but the bitty shapes this time are slightly weird. So we slice, actually you couldn't really slice this in this way that I'm talking about, but I'll say make slices along the x-axis and rotate or revolve each. So what I am imagining here is, think about the area, just the area that I'm talking about, and slice that area into rectangles as you would if you were just finding the area, right? Slice this area into rectangles. Those are the slicey bits. But then each of those rectangular slices, you revolve around the y-axis. And the shape that you get is, I scrolled it away, a cylindrical shell. So each of these little rectangles, each rectangular bit gets revolved around the y-axis and becomes a cylindrical shell. What one of these would look like is, I have my shape here. I pick out one little rectangle like that and revolve this rectangle around the y-axis. And what it looks like is this kind of a thing. It's a very skinny cylinder, which is what they call a cylindrical shell. I hope everybody can visualize the kind of shape that I'm talking about. And then the total volume will be the sum. You add up all of the volumes of these very thin shells. So in order to get the volume, I have to first of all figure out what is the volume of each one of these little shells. So this, I think of this thickness as being like delta x, and then it has a certain height, but this height is given by the function f of x, right? And so what's the volume of one of those shells? It will be something like the, if I were thinking about this in terms of, this is basically like a circle, right? And it has a certain circumference. The circumference would be given by the radius as measured from the middle, which is actually not the function f of x, but it's just the straight up the x value, all right? So this shape, this is like a circle with circumference pi times, it's 2 pi r is the circumference, right? But the radius that I'm measuring here, this radius is just equal to the x that I'm considering at any given point, all right? So it's like a circle with circumference 2 pi x. To turn that into a volume, I need to multiply by the thickness. So it's a circle with circumference 2 pi x and thickness delta x and some kind of a height to it, right? And the height is given by h, which is f of x, all right? All told, the volume of one of these individual shells, so the shell volume is 2 pi x times f of x times delta x. It's the product of this circumference times its thickness times its height. 2 pi x times f of x times delta x. And so the formula, when we turn this into an integral, it's about time to go, but I'll just write the formula. So the total volume, when you actually add up all the little shells, will be the integral from a to b 2 pi x f of x dx. The delta x kind of turns into the dx when you do the integral, all right? It's a strange formula just because it's almost just the integral of f of x, but not quite, because you got to also multiply by x. But one thing that's nice about this formula is it doesn't have a square in it. Sometimes when you're doing the shells method, sometimes when you're doing the washer method, that extra square messes it up. In our cases, we were doing polynomials, so you can do the FOIL and handle the squaring, but sometimes the square really screws everything up. And this one is an alternative which doesn't have the square in it, but it does have this extra multiplication by x, which you have to handle in different ways. But anyway, that's what we'll do next time. All right, please let me know if you have more homework questions. I'm happy to talk about it.